Let's quickly see projection of one vector onto another. We have seen uh, what a vector is, addition and the difference of vectors. So let's quickly see the projection part now. So let's take over here, we've got x bar, y bar, and we see that the vector x has been projected. You dropped a orthogonal projection, you dropped a perpendicular onto y, and then the resultant, you've got a vector z, right? You've got this vector z, and you want to know what is z, right? Because that's the projection of x onto y. So here we could start off with the magnitude of z and then the direction of z, because every vector, if we can determine its magnitude and direction, we've kind of figured out the vector itself. So if you look at this right angle triangle over here, and if you say, okay, let's just write some things down. So projection of x bar onto y bar, we need to find out this, and for this we need the magnitude of z and let us say the direction of z, unit vector, right? So here you have modulus z or magnitude z from this right angle triangle. You can easily say it is equal to the magnitude of x into cos of theta, right? Why? Because cos theta is equal to adjacent by hypotenuse, and as soon as you see, and it's really like when you see theta, cos theta here, we really don't know cos theta, right? More often we would know other measurements than the angle, and we would kind of figure the angle out. So let's try to find some other way, and as soon as you see cos theta, we get reminded of the dot product, right? The cosine of this and cosine similarity and all that stuff. So the dot product. So dot product is what? Magnitudes of the vectors into the cosine of the angle between them, and if they are perpendicular, is 0. So here cos theta is this, and we can kind of replace cos theta using a dot product to say cos theta is equal to the dot product divided by the magnitudes of the participating vectors. So this goes straight away, and what you've got is dot product divided by the magnitude of y. So in short, the magnitude of the projected vector is the dot product of the two vectors divided by the magnitude of the vector that is being projected on, or the vector that's bearing the projection, so to speak, right? So that's magnitude of y. Now let's quickly come to the direction. And now we know, or if you look at, before we go to the direction, so we can say that the vector z itself is something like a prod magnitude into times the direction. That is, if you choose a particular direction and you traverse that direction magnitude times, then you get this particular vector. That's the way I look at it. So here we know the magnitude is this, and direction over here is actually the same as the direction of a vector y, or original vector y. And why is it same? Because the z is literally on y, let alone being parallel, it's literally on y. So here you have mod z divided by that is y bar, right? And then from here we know mod z is x dot y divided by magnitude of y, and over here we've got y bar magnitude of y, that's equal to dot product divided by magnitude of bearing vector whole square into this one. So if you just quickly calculate this, dot product is what? 3 into 10, 30, 24, 54. So that's x1, x2 plus y1, y2, right? So that is 54 divided by magnitude of y is root over 10 square, 100, 6 square, 36. Root over 136 whole square is equal to 136, and you've got y bar here, which is 10, 6. So this actually we are done over here. This was the formula over here. This is our derivation, and we can just say the vector is basically the dot product divided by the magnitude of whole square and into this. And if you actually see, this makes sense. This makes sense actually. So what we are basically saying over here with this is we have some scalar into the direction of we have some scalar into y, right? And since this is smaller than y, we can say that this scalar would be less than 1, so that's to decrease it from here, right? And if the projection, if the x bar was somewhere here and if you projected it here, then we could say that this is greater than 1, right? So in this case it would be decreasing y bar and shrinking it to here. So let's see if that's happening, right? Let's just go through this just for the sake of completing what we have done. We're anyway close, so if you have to simplify this, this would go 2 6s, sorry, 18, so yeah, so 68, and then over here this is 17 and 10 comma 6, and yeah, this would be 5 34, 5 17s, 5 17s, 5 85, 85, and over here again 34, 3 81. So yeah, this is our final z, right? 85 by 34, 81 by 34. And if you see 85 by 34, what could be 85 by 34? 34 3s is 90s, 2s is 60s. So here, so it's 2 point something, and over here 85 by 34, yeah, it's also 2 point. So if you see our point is somewhere 2 points, so there, so if you see it's wrong, something is wrong here. So we have done something wrong over here, right? So 17, 20, yes, okay. I think okay, yeah, 27, right? So this is 27, and this would become 7 divided by 68 into 10 comma 6 is equal to 34 here and 5 up here, 5 7 5 35, 5 3 10 135 divided by 34, and over here again it's 34 and 3, so it is 81. So this looks much better actually. So 34 into 3 times 9, yeah, somewhere around there. 34 3s would be 34 4s 16, 4 3s 12, 136, right? So let's say it's equal to 4 comma, and this is again 2 point something. So if you see here, yeah, so this looks much better. So if you see it's 4 and 2 point something, yeah. So yeah, so this is what is that projection, and how you can calculate the projection of one vector onto another. And it's quite important why we need this, because now let's say we've got this point 4 comma 2.1, then we can calculate this distance, right? And you would see in certain algorithms that we really need this distance, right? Like if, for example, if this was a plane and we want to know the separating distance from a point to a plane, and that we know here by just, the magnitude of this is just 3 minus 1, 3 minus 4 whole square, that is 1 square, right? This is 1 again, so, and 4 minus, let's say it's just 2 whole square is again 4, so it's equal to root 5, right? So yeah, so that's what is the use of a projection.